Hello, Robert. I can't hear you.
Does it work now?
Now it's okay.
Hi.
Nice,
Nice to meet you.
nice to meet you too, Robert. So today we start at 12 and we had two lectures already today. One of these lectures was just overview. Some PhD student told them about their opportunities in different countries. It was about Israel. Then they had kind of a lecture about new reactors. And now I think you have kind of a seminar, right? So you will focus a little on the science, but you can also tell them about your institution or whatever like that. It would be nice also.
I will just mention it at the end. Also, let's see how much time. I'm going to try to not speak for too long.
Okay.
Yeah. I will tell them at the end what kind of opportunities they might have at our institution if anyone is interested. Yeah.
Nice.
Mhm.
So how it's going in Romania? Why Robert left? Why Cyprian left? Sorry.
That's a good question. we keep asking him, but he.
Because I just was kept with him in touch on Facebook. I
Mm.
have posts connected with at university and whatever, and I thought he is there and in an academia, but
I
I contacted him. He said I'm already not there. I was kind of a bit shocked, and then
to be honest, we were also shocked because I mean he also I mean I don't want to gossip because to make anyone to tell, but he I mean he had he won a postdoc, and after that I mean there was the opportunity for him to get tenure track at our university. I don't know why he didn't want to. I don't know if there was some discussions or I don't know. He just said that he doesn't want to continue anymore. I was surprised because it was but
Okay.
yeah.
Okay, so you are doing PhD or you already finished it?
I finished. Yeah, I finished some while ago, a few years ago. Yeah,
And,
but I did my PhD in theoretical physics and moved into solar energy stuff afterwards. So
mhm.
I did my PhD at the same time as Ciprian.
Okay.
Yeah.
And do you teach in the university or just a the researcher? Do you have
Uh,
teaching
well,
activities?
now from last year, I have a researcher position which doesn't have any teaching in the norm, or how do you say it. But yeah, I've taught some labs
Mhm.
uh, in one semester, and I've kept teaching since I've had the since my PhD.
Mhm.
Usually labs.
And your lab is kind of department of university, right?
Well, our faculty is pretty small, so we only have one department that covers everything. But we have a research center, or how you call it.
I say department is very small. It's how many people?
I think we are 24 people in total at the
How many?
faculty.
How many?
24, I think. University.
It's
Uh,
like in our case, it's at the level of the department. So we have
mhm,
like School of Physics and Technology, and we have four departments, like 24 people each. But they are still can be involved in teaching or
mhm.
research. So we have research positions and we have teaching positions.
I mean, for us, it's kind of new because at our university, normally, so a while ago, they started introducing this research assistant position, but it's like for 3 years.
Mhm.
And after that, they didn't have any tenure track researcher position, although it exists in formally, but no one was hired as a researcher.
Mhm.
I think there was one person after 89. There was only one person who was hired as a researcher, but I don't know. We didn't have so many students, but we also have good research results. So I think this is why they.
Exactly the same situation in our case because we have high level of science of recognition, but
Exactly.
we don't. Now we have to start like in first level, first year of a bachelor's degree, and we don't have too many applications. We just have like 10 applications.
Mm.
And for example, when I was studying at the same level, I was one of 150 applications. So take a look the difference. But I'm not too old, you know.
But
Like
this because of the war, or just this is the
no,
trend
it's
for
not
so many
because of
years?
the war. It's just about the decline in
Mm.
interests, I think, in
Yeah,
medical science.
but
That's
that's very steep decline. I mean, we have like 60 something positions in the three bachelor specializations at our university, at our faculty. When I was, it's been the same number like for many years now, and most years you manage to cover it, but just barely. With the masters programs, it was always a problem to get enough students. But now in the last years, we have been starting to not
to increase.
manage to cover all of the bachelor degrees positions completely. And also many people, because we don't have admission exam, a lot of people
So,
apply.
so actually everyone can enter, right? Like
Yeah. So what happens is that like at least a third of people enter just because and all of our students get a dorm. How do you say it?
Okay, yeah, I understand.
So people sign in, apply for us, but then don't really come to courses and stuff. So I think like one third of the people are like this. So maybe we have 40 people, and of those 40 people who are like interested in the university, of those 40 people, and maybe 20 if they manage to finish. Most people get a job, don't
Yes, and
actually.
year after year, some
Less
part
and less.
less and less. Okay, yes, that is
Yeah.
the same in our case. So we have 10 students at masters, and for PhDs we have like in general maybe we have 10 PhDs, but in department we have like 2 or 3.
Mm. Yeah, normally it's like this for us also, I think. And the master's degrees are really struggling to to find enough. We're applying all kinds of unorthodox
And
tactics to
what about, by
fi-
the way, what about, for example, international, maybe, I don't know, by the way, teaching in English is okay or not? You don't do you have any programs in English like that?
well, officially our master's is in English, but
Especially in English, right?
uh, I think we only teach in English when there's some international students. Not usually there's some, one or two, maybe three, four in each year. No, not a
We
lot
have
of people.
very similar situation.
Mm,
So is they are not too much,
mm.
not too many people, right? So you just need maybe that is the point.
Yeah, but we have like interesting programs. I mean, both for masters and like for the PhD program, I think usually the rule is that half of all applications are funded with uh, how do you say bursa with funding, you
Mhm.
know, and so it's pretty good. The pay is not so good for PhD students. That's true, but and we also have like two postdoc positions, but this is on the whole universe, or I think on the real sciences. But they are very well paid, so they are meant for people from
Yeah,
outside Romania.
yeah, that
But
is.
this really might be interesting for your students to
So
think about if yeah.
okay, okay. So Robert, maybe I'll go and take a cup of coffee and we'll start in 5 minutes, okay?
How let me just ask, I don't remember, how do you blur your background with
Okay,
blur
you
my
should
background, yeah.
switch on
Yeah,
options,
this,
right? Yeah.
yeah, I managed, yeah, thank. Okay, then I'll be back in 2 minutes also.
Yeah. So we started maybe 2 or 3 minutes after 12.
Okay, sure.
Mhm.
Mm-hmm.
Андрей, попили кофе, да? Нет, Андрей.
Я услышал.
Maybe we should have tested also if the share screen works.
Yes, you can try it now. I
Let me
can.
just try. I think starting the PDF would be.
Yeah.
Is it okay now?
Yes, we can see. It's nice.
Oh.
Robert, we should wait maybe for several.
Of course, of course.
And then we'll start. Previous lecture was 20 minutes more than scheduled, so the break was maybe too short for students. They had only 40 minutes break instead of having 1 hour.
How about was it planned for them to have 1 hour?
Yes, it was planned to have 1 hour, but they had only 40 minutes.
Yeah, from 11. Yeah, sorry. I thought it was an ongoing session from 9 until the.
No. It wasn't the one, so we did a break. That's why we're waiting for people.
Maybe they're also seeing that is something about photovoltaics, and they're thinking that it's some applied. Because we always had these jokes. We always had these jokes between my department. Before I worked in theoretical physics, we had these jokes about people working in more applied fields. So now I'm working like in modeling, which is like semi-applied. And
Okay.
so.
Hello.
Let me take a look to the list of students. Насти нету. Есть Осипова. Нет, больше нет. So maybe let's start anyway. We waited for 5 minutes. Maybe others will join us later. So the second part of today's practice is a seminar, which is provided by Robert Blaga, who is the representative of Faculty of Physics in the University of Timisoara, which is in Romania. And he'll tell you about his research activities. The topic of his talk is solar energy modeling for PV power generation. And maybe you will be able to ask him questions about the university or opportunities in his research area. So Robert, please.
Thank you. Let me just share the screen. Start the presentation. Thank you so much for the invitation and for this opportunity to talk a bit about the topics that we work on in my group. My name is Robert. I work at the West University of Timisoara as a researcher. I finished my PhD a few years ago in theoretical physics area and quantum fields on curved backgrounds. But since then, I have moved to the field of solar energy, which is like a big transition, phase transition. Yeah, and since I worked on the topics related to solar energy modeling, which I will talk a bit about today. Okay, so in the first part, like 10 minutes, I will talk just some basic stuff to introduce the problems that we are facing, and then talk a bit about actually the content of our research. So generally in this field, there are like maybe three big questions that are being posed. One is the first, or the main one is like, given that we know how much the extraterrestrial radiation is, the radiation at the top of the atmosphere, how much radiation falls on a given PV installment, whether that's on the surface of the ground more often or in space, then we are facing different kinds of problems. And in order to model that, we need to model in some way the impact of the atmosphere on the incoming radiation. So this is mostly what I will be talking about. But just to mention, there are other kinds of questions. First of all, another question is under ideal conditions, what is the efficiency of a PV cell? This is more applied research, trying to develop new materials that have either higher efficiency in converting the incoming solar irradiance, or even if it has lower efficiency, having some other kinds of properties, like a cell which is transparent to visible light is good to put in the window. So it works passively, even if it has a smaller efficiency. But we work like only minimally in my group on this topic. And the third kind of topic is given X amount of energy that falls in each second on each square meter of my PV array, how much energy does actually the PV installment produce, my PV plant produce? So we work mainly on Q1 and also on Q3 in my group. And also, just to fix some terminology, the way I use the terms, usually I say predict or prediction, which is the most broader term. And there are two kinds of prediction that we deal with. One is estimation, when you are trying to predict what a given quantity X will be at the present time T, as a function of other quantities at the same time T. For example, how much power is my PV cell producing given that X amount of solar radiance is incoming on it. That's estimation problem. And the forecasting problem is that given that we know past measurements of a given quantity, let's say the output power of a PV array, how much energy, how much power will it produce in the future? So this is a forecasting type problem. We work on both. I think I'll focus mostly on estimation problems here, but yeah, and also so to focus on the first kind of problem, this is what we work on most of all. Given that we know the extraterrestrial radiation, this is just simple physics, then how much radiation will arrive at the ground? And there are different routes through which it can arrive at the ground. If you have an incident solar beam, part of it will be scattered or absorbed, and a fraction of it arrives to the ground. This is what we call direct solar radiance or beam radiation. We see in this illustrative plot, we see this is the beam radiation. And the second component is diffuse radiation, which arrives through any other means to the ground. So it can arrive through scattering on clouds, scattering on aerosols. If there are mountains with snow on them, there can be reflection of the mountains. Or if the ground is highly reflective, then you can have reflection of the ground and other kinds of effects. You can have also backscattering effects like reflection of the ground, reflection of the clouds, and then arrival on the PV fan. But these get, as the order of, as the number of reflections increases, of course, the contribution decreases. So we say that the total amount of radiation or the global irradiance is equal to the direct irradiance plus the diffuse irradiance. So the problem is usually to model in some way either the total irradiance or the components. So just to catalog a bit the processes that we need to keep track of, the most important factor which clearly affects the incoming solar beam are clouds. We need to know how much clouds there are, what kind of clouds there are, all these kinds of parameters, information affects how much radiation arrives to the ground. But then the second most important atmospheric species are aerosols, which is any kind of particle which is nano or sub-nanometer in spatial scale. It's important to know what type of aerosols we have, how much amount, what kind of distribution we are talking about, etc. Then the other two important factors which contribute to the extinction of a solar beam to the atmosphere are water vapor and ozone. And then there are some more less important ones: NO2, carbon dioxide, carbon monoxide, methane, other stuff. It's important to it's important to maybe to say that it's interesting that carbon dioxide and methane, which we know that have an important role to play in global warming, actually have a minor role to play when we are talking about the extinction of the incoming solar beam. You know, why is this? We can remember that the average temperature of the Earth is around 15 degrees. And then if we think about the black body spectrum that it emits, its maximum is somewhere in the infrared, where the carbon dioxide and water vapor and methane and other species have absorption bands. But for the incoming solar beam, which is has its maximum in the visible spectrum, it's not largely affected by methane and carbon dioxide. It is to an important degree by water vapor, just to figure this. Maybe if you can tell me when I reach like half an hour or something, so I don't speak too much here, or if it becomes too monotone.
Yes.
Yeah. Okay. Yeah. Just now. So these are
Actually, guys, students, if you have any questions, maybe you can
of course.
interrupt Robert and ask him if something.
Please interrupt me at any time. I will not see if you raise your hand. Maybe you can help me to moderate if anyone has any questions.
Yeah. Okay.
So these were the components of the atmosphere which are important. So maybe just to jump back to say that physically the process is radiative transfer to the atmosphere. So if you want to physically model the process, then you need to solve the radiative transfer equations to the atmosphere. This is just as a frame. Yeah. And so there are three different approaches to modeling. The first type of approach is like simulate or modeling the full physical system with physical equations, no approximations, or maybe approximations but analytical, not qualitative approximations. So there are also different kinds of physical models. There are a type of model which are called numerical weather prediction models. These simulate the whole atmosphere, the kinds of simulations that you see done by NASA and also by your weather organization, meteorological organization and stuff. They simulate the whole atmosphere with a lot of the actual components and with pretty good information about the initial distribution of substances, molecules in the atmosphere. Of course, they suffer from the fact that the time scale is like 1 hour usually, the time step, and the spatial scale is like 1 per 1 kilometer at best, usually 10 per 10 kilometer, 3 per 3 kilometers, the resolution of the spatial grid. So for smaller effects, of course, they are not that useful. But these kinds of models have global coverage. That's important. Also, other kinds of physical approaches. For example, if you know how much solar irradiance you have under a clear sky, then how can you model the effect of clouds? And one approach which I will talk about is if you have images of clouds and try to determine the speed and direction of the movement of clouds. So that's a physical approach because it relies on the physical dynamics of clouds. You're not watching only time series of whatever parameter and working with statistical properties of these quantities. You are relying on the physical dynamics of the components of your system. Okay, so there are some, for example, other models are empirical models. These are actually just you have a parameter which you are wanting to estimate, and you just put in on the right side some other quantity and some fixed coefficient or some coefficients, and you fit this equation on the data. It doesn't need to have any relation to the physics of the problem. So you can try anything you want. These are fully empirical approaches. Maybe I will talk a bit about, in the end, about what is called separation models, if there is time. And the intermediate approach is what are called semi-empirical models. They, in some way, approximate structurally the physical equations, the physical solutions of the full physical system. But at one step, you lose physicality because you make some approximation, introduce some fit parameters. Yeah. So, for example, a semi-empirical model to estimate the solar irradiance under clear sky would be like from this plot, would be a mapping from the yellow profile, which is the extraterrestrial radiation, onto the orange profile, which is the irradiance that reaches the ground. And you see here the bands which are missing because of absorption by water. And the infrared, you see some contributions from carbon dioxide. But here, mainly in the visible part, you have the effect of aerosols and water vapor, and to some degree ozone, which is affecting the radiation that reaches the ground. Okay. Just a few things about our experimental setup. We have a solar platform we have an experimental platform on the roof of the university building. I am showing you just a part of the measuring devices that we have. Different kinds of PV cells, differently orientated. This is also an important aspect to watch to what degrees you are orienting your PV cell. It influences how much energy you can collect. We have pyranometers, which measure the components of the solar radiance. And also, more recently, we have acquisitioned a fisheye camera, which makes pictures of the sky. I will talk a bit about this later. You can say something about the movement of clouds from these images. And also, just to mention here that it's very important that in this field we have a lot of sources of public domain data, because especially like Romania and also Ukraine, where we have less financial resources, it will be very hard if everything would be behind a paywall or you need to pay for a license to use this data. But a lot of these sources of data are public. Ground measurements, satellite measurements, and also these numerical weather prediction results. For example, NASA makes its simulations, I think, the other day or immediately publicly available. So that's incredibly useful for doing research. Okay, now to get a bit more into the research part, for example, on this slide, I will talk a bit about how you model aerosol, the impact of aerosols. First of all, an important aspect is what kind of aerosols they are. let's just say that generally a solution to the radiative transfer equation is something of this form: an exponential minus a parameter and an optical depth. So this is, you can write such a solution for each species, each component of the atmosphere. This m measures the path that the radiation is taking to the atmosphere, so the thickness of the medium in physical terms. The aerosol optical, usually these optical depths for the different species are discrete or non-zero only on discrete subdomains, because they pertain to where the absorption bands of the given molecule are. So you're not analytical functions. It's very difficult to work with them. You can work only numerically with them. But for aerosols, we have, because we're not talking about absorption bands or something, we have an approximate equation which is universally used. It's called the angstrom equation. So the dependency of the optical depth is with the wavelength lambda of the incident radiation to a power. Alpha and beta are coefficients. Alpha is inversely proportional to the diameter to the effective diameter of the aerosol particle, and beta, among other things, holds information about the number density of particles that you have. So, I mean, this would be up to this point. This solution is physical, but it's very hard to work with. So you usually do this approximation of the angstrom equation, which is already an approximation, and then more commonly what you do is replace these spectral transmittances with a broadband transmittance, where you integrate out the wavelength, the spectral dependency. Of course, you lose physicality here because these averages are not exact. So, I mean, I will need to explain a bit more, but I don't want to waste time here. But you lose physicality here, but tests show that these are actually pretty good models with these replacements. So you integrate out the wavelength dependency with a weighted average, and the weighting is with the profile of the extraterrestrial radiation. Yeah, and with these quantities you can work numerically, because you still cannot do these integrals. You can work either numerically or do a fit. So you take an exponential equation and fit some parameters here, A, B, C, D, which are then, of course, you lose physicality, but are easier to work with.
How to choose the form of the fit?
Well, you can choose any function you want. Basically, the closer you are to the physical solution, hopefully the better your fit will be. But you can try to force any function you want. So usually you know that the form of the solution of the radiative transfer equation is this kind of exponential. So you usually choose an exponential of this form, but it's not usually universally valid. So sometimes you do some polynomials. You can actually try to approach it analytically. So, for example, try to replace the transmittance function with, but I think you need to replace both the extraterrestrial irradiance and the transmittance with Chebyshev polynomials or something else, and then truncate the sum, and you can somehow work out how the first terms actually, work out or something like this.
So how many parameters are there in your modeling function?
Are you asking about physical parameters or the fit parameters?
About fit parameters.
How many you want? You can put how many you want, obviously.
So, as far as I understand, you make approximations based on the numerical solution to this distribution, correct?
Based on the form, based on the structural form of the solution, not the numerical. Yeah. So you fit, of course, based on the numerical results of this integral. Yeah. Here you mean, yes, exactly. Yeah, but the form that we take for this fit function structure is similar to the physical solution. That's why it's called semi-empirical model, because you use some information about the physical solution. But yes, it's fitted on data. But it's important that these optical depths depend on several things, but the basic thing, basic coefficients, the diffusion coefficients, or how they are called, are depend on material properties. So you can find them in the lab, and then you need to also multiply by the amount of that substance which is in the atmosphere. But the coefficients themselves are material coefficients, so you can find them in the lab. But still, they are a discrete. They're not an analytical function. The result is not an analytical function. So you either have the choice of working numerically or of doing some kind of fit. So we try both, but usually we work with this kind of fit for the. You will see that in some slides from now, you will see that instead of this more natural exponential, we try just some polynomials. Yeah. Just to say a little bit more about aerosols before we move on. The problem with working with aerosols is that unless you have a plane to fly in the atmosphere and take samples or something, you have only information from the ground or from satellites, and that is optical. So what you have information is only about optical properties of these aerosols, and from that you need to, if you want to say something about the nature of the aerosols, that's a research problem in itself. How to deduce from knowing this alpha parameter, beta parameter, and some other parameters. For example, here you have the single scattering albedo, which controls how much the aerosol scatters and absorbs. So from these, somehow you need to deduce what the type of aerosol there is. Usually the main kinds of aerosols are urban industrial, which result from different burning processes or anthropogenic burning processes, desert dust, biomass burning products, smoke and stuff, and marine salts. These are the four main types of aerosols that we are dealing with. And so it's interesting to see in this plot. So it's emerging from the literature that the best way that they separate in terms of optical properties is if you plot it in this plane. The alpha parameter from this angstrom equation and the single scattering albedo. You can see nicely that single scattering albedo of 1 means 100% scattering, and as it lowers, then the absorption becomes stronger. So you see that for marine salts, which is these blue dots, you have almost 100% scattering, and because alpha is small, it means that you have larger particles on the order of micrometers. That is what the size of these particles are. So up to a few nanometers, up to a few micrometers, and then as alpha increases for urban industrial aerosols, you have below 1 micrometer, 0.1, 0.01 micrometer. This is the diameter of these particles. But you can see that nicely they separate here in this plane. Okay, maybe I will move on. If you have any questions, please interrupt me. I will move on. Yeah. So for example, you see here what an example of these fit equations look like. I've shown you only for aerosols, but the same can be done for every species. So you see that we consider aerosols, which is Rayleigh scattering, which is deducible up to some point analytically. Little g is the collective impact of trace gases. W is water vapor, and NO2. And so you see that most of these are polynomials. And the way that the transmittances just multiply because the extinction processes are independent of each other. So the beam transmittance, the complete beam transmitter is just a multiplication of each individual transmittance. The diffuse part is more complicated because, as you've seen from the plot at the beginning of the presentation, you have different processes that contribute, and they are more difficult to model. But just to show you that this is how a result looks like, you have measurements, and then you have the modeled solar irradiance, let's say the global irradiance or the direct irradiance, and then you compare them through different kinds of indicators. Mean bias error is just the mean error, and root mean square error, this is an indicator which taxes like very large individual errors. And you can have a plethora of other kinds of indicators which capture different aspects of the accuracy of the model. Because when you have a problem, an application, you want a model to be good at doing something. So you have different kinds of accuracy metrics capture different properties. So you need to tune very well what the error metrics are. If you use an incorrect error metric, you can find that your model is very good, but in fact does not do what you want accurately. Yeah. Okay. Yeah. Just how are we doing with time? If I can ask.
Yes, so if you have maybe 20 minutes, because we
Okay.
typically make a short
Yeah.
break before the next speaker. So
Yeah. Sure. You're good.
you can do it like 15-20 minutes, and then some
Okay.
space for questions, and then
Yeah.
speak. Okay.
Okay, I'll try to go. Yeah. So I just have a slide here about stuff which I'm working on currently, which I'm very interested in. There's like you see on this plot is a map of Timisoara, color coded or different land use, types of land use. Blue is residential, green is parks and green fields, and red is industrial areas. And so a type of a question in the orange dots and the red dots are two networks of aerosol sensors, but at the ground level, so not in the whole atmosphere, just on the ground level. And so one interesting type of problem is to model whether you have larger concentrations of aerosols close to industrial areas. This is a typical problem of study. But it is mostly related to health stuff, but also it's important for
Robert, sorry, so that is the map of your sensors, right?
Oh, it's not ours. These sensors are, we have some sensors, but these are the sensors of the administration.
But you receive data from them, right?
Yes, they are public. So these are also public. Yeah.
Okay.
Yeah. So if you want to work with them, you can also access this data. This is very good. And so there are different kinds of problems which are interesting. So first of all, for solar energy stuff, we are interested in not what happens at ground level, but in the whole atmosphere. So you can develop the analytical with some approximations. You can develop analytically the relation between the concentration of aerosols at ground level and the whole effect in the atmosphere. So that's interesting to study. You need more information about the chemical properties of aerosols. If you don't have that, you can try to model empirically, but this is the whole field of research, and I am working on this currently. Don't have any results to show because I don't have any papers published, but this is what I'm mostly interested in currently. Yeah, and there's all kinds of stuff which are interesting to model, including, like, for example, these kind of pollution levels at ground level are mostly important for health reasons, of course. But they're also important for solar energy stuff, because if you live close to a plant which is emitting smoke and you have a 4 PV panels on your roof, it's going to, cut like with 17% your energy production. So that's also important to be able to quantify. You can actually put an economic value, a financial value on the loss that you are suffering because of your proximity to this factory or something like this. So these are kinds of topics that I'm looking into. Yeah, and now just the final part to talk a bit about the cloud field modeling part. So we have this camera since we have this project. My professor had this project which just ended. So I've been working on this topic for 1.5 years now. This is the whole experimental setup. I'll just move quickly. But this is how on the bottom right, this is how the initial images look like. These need to be processed. Let me show you how the stages look like. So again, here on the left, you have the how do you say the initial image, and then these are various stages of processing. I have tried to work either with these intermediate data files or with these binary data files. In the binary data, you have either a 1 or a 0 associated to each pixel, which means it has clouds or it doesn't have clouds. Of course, it's a simplification. And so what I do in this approach, I don't know why normally this should be looking simple like the others, but there's some problem here. But we introduce this kind of polar grid, as you can see in the bottom images, and then we calculate for each sector, for each grid cell, how much, what fraction of it is covered by clouds, then calculate changes over different steps, and then some way try to calculate from this to estimate the average motion vector of the clouds. And then the direction, then the whole cloud, the whole image is advected in the direction of this estimated vector. For example, if the vector is like this, then you move all of the cells, all of the clouds in that direction, like the pink cells are illustrating here. I would just jump here. This is how the end product, how a model looks like. You use those those forecasts for the motion of clouds. You introduce them into this model, which is forecasting the solar irradiance, and then you can tell basically the important step which the clouds are bringing is a physical explanation, physical prediction whether the sun will be covered or not by clouds, because you can see in the picture on the right that when you have clouds, these peaks are moments when clouds pass in front of the sun or near the sun. So you need to be able to foresee these, because if not, of course, you have huge losses in your production. The problem usually is, let me see what I have here. I'll jump over just to say that if you're an energy producer, there are two kinds of forecasts that you need to do. One of them is like today, if you want to participate in the market to sell your produced energy, you need to make a day ahead prediction, meaning like today at 10 a.m., I need to make a prediction for tomorrow, starting at 12 a.m. at night until the next 12 a.m. In hourly values, how much energy I'm going to produce each hour. That's already a hard prediction. And the second prediction that you need to do on a continuous level as time passes is like on 15-minute time scale, you need to be able to produce like for the next 15 minutes and the next and the next for 3 or 4 steps ahead. So these are two types of forecasts that you need to do if you are a PV producer and want to participate in the market. So these are the most important types of forecasts that we need to capture. Okay, I would just jump over this. This is another example with the same model, but directly predicting the power, not the solar irradiance. But for example, what we can see from here is that with this cloud model that we have developed, starting from 15 minutes, our models become very good. So that's actually perfect, because the 15-minute time scale is exactly what the market uses. So what you need to participate in the market. So we are very excited about this result, and even though this is again like quite basic result, because we were working like only for a year on this cloud forecasting algorithm, and still it produces like quite good results on 50-minute time scale. Yeah, I think I will stop here. I have another slide at the end if anyone has any more questions, but let me.
Okay, so
yeah. Please.
What is XI-T? Like it's Kronecker?
No. So this Xi, the Xi is a binary parameter, which so there are two ways you can quantify your forecast of clouds. Either how much of the whole sky is covered by clouds at the forecast horizon, or whether the clouds will cover the sun or not. And this Xi is a binary variable which says whether the sun is covered or not by clouds. You can see from this plot, the green dots are the actual measurements, with the 1 means that the sun is not covered and 0 means that the sun is covered by clouds. There's a way to quantify this, of course.
Okay, so just whether it is covered or not, right?
Yeah. So in this model, we have used the information about clouds to predict this binary variable. Yeah. So that is Xi. It switches between two regimes of the forecast model, the upper branch and the lower branch. Yeah. Please ask more questions. I will leave you with this. It's just very interesting. Working on these images, on this cloud images, also brings up questions about philosophy of science, because normally it was not my job to look at these images, yeah, like you always need to do a maintenance job to check if everything is okay with the images and stuff like that. It's not my job. But I kept seeing like in the processed images, you see like only these white clouds, white blotches on the in the data, and sometimes you can see like blotches which do not move at all, and like what's happened, or some that jump around. And first I thought they were physical. There were physical clouds that do something weird, and they kept introducing huge errors in our data. And then actually, after I started looking to the images, I actually found out there are different kinds of insects and animals which are moving. And so this is an interesting observation for the philosophy of science, because of course I was able to look at the truth because I was able to look at the images, but usually you have access only to the information which is filtered through a model, right? And so if you are talking about gravitational waves or stuff that's happening on the quantum level, you always have access to the data only filtered through a model. And yeah, this illustrates how that can fail if the model is not accounting for some effects. Yeah. Yeah, I think that's all. I have one more slide if there is time, but I don't think there's any point. If there is any questions, I will talk some more.
Yes, okay, so I actually see that Axel is already with us, but maybe for now anyone has questions to Robert.
Well, if I may, it's not a question, but thank you for the presentation. It was very interesting to see such an angle at this problem, because normally we don't think about predictions when we speak about solar energy and such stuff. It was very new for me to think about predicting clouds and forecasting the energy output like in 15 minutes time and longer.
Okay, thanks, Andrei. So it was just a comment, like not a question, right, Andrei?
Yeah, just thank you.
Thank you for the Thank you
Okay.
for the comment. Maybe just before there's another question, just to say if anyone is interested, also about collaboration. I'm not sure, maybe of your students, if someone is interested. Especially, I'm working on this urban stuff, which if someone is interested, I need people to collaborate with. That's on one side. And the other thing that I want to say is that at our university, we have a master's program, which is particle physics and computational physics. This is the most relevant for the context here. And funded PhD programs. I think like half of all PhD applications are by default funded by the state. So if that's something you're interested in, and they're also at the level of the university, there are two paid, well-paid, I should say, PhD, not PhD, postdoc positions per year, mainly for people who are outside of the institute, outside of Romania mostly, so international students. So if anyone is interested in that, just please write to me and I will give you more information. Yeah.
Okay, so actually, Robert, our students have just finished 3 years of bachelor's, and for now they are kind of looking for a supervisor for their bachelor's thesis. And maybe it would be a good point for somebody to start contacting with you and maybe write thesis first, and then you can look for masters and PhD and whatever like that later on. Okay, so if somebody wants to contact Robert, it's I can give you a contact, etc., etc., like that. Okay, maybe more questions to Robert, guys. No more questions. Okay, so thank you, Robert. Thank you for your talk. Axel, I see Axel is already with us.
Thank you for the invitation.
Yes,
have a nice day.
Axel, you see, we should make a short break for maybe 10 minutes.
Absolutely. It looked like the schedule is very packed today. A lot of talks in a row.
Not too much, just 4, but maybe for students it's too much. We had the 2 previous lectures in Ukrainian. Now we have like English part, so
you save the English for when at the end of the day after everyone's exhausted.
Okay, so when should we start? Maybe let's start according to a schedule. Let's make a 15 minutes break for coffee and whatever, and start at 1 p.m. Ukrainian time. Okay.
All right, plan to talk to you then.
Okay, so let's start at 12. Okay. Okay, so maybe we should start our last talk, guys. So today you had 3 lectures at different institutions, and the last one is for Axel, who is the representative of George Washington University in the United States. We have some alumni from our department working there in the United States. It's Mr. Afanasyev. He is the leader of research groups there, and Axel actually works with him in this university. And he will present us the overview of experimental nuclear physics at George Washington University. So please, Axel, you can.
Okay, I'll share my screen. Hopefully that comes through for everybody. Does that share okay?
Yes, it's okay.
Now let me ask, is everyone viewing this remotely? Is anybody on the campus, or is everyone logging in from their computer?
I think
From computer.
Okay, good.
so we're not able to be somewhere in the campus. Everyone is located in different places, and everyone is looking from their own computers like that.
So since we're all going to be doing this online, it's obviously hard for me to gauge if I'm saying things that no one is understanding, and it's hard for me to gauge if people are curious about things. And I just encourage you to feel very comfortable interrupting me, very comfortable stopping and saying I didn't understand, or I'd like you to say that again. It's really be my pleasure to pause and go back.
I have a question.
Please.
I noticed besides your name, Axel Schmidt, there is pronouns.
On my email?
Yes.
Mm-hmm.
Oh, okay. Understood.
You're asking about my email signature?
No. On your name in Zoom, it says Axel.
Axel Schmidt. Oh, he, him on the Zoom.
Yes.
Yeah, that's becoming fairly customary in the United States, where there's lots of names of different national origins, and sometimes it's not clear which pronouns are appropriate for which speaker. And so it tends to be a courtesy, and most people just add them, even if it's not ambiguous, to just make it comfortable for people for whom it is ambiguous. So that's why.
Understood.
It can be very difficult. For example, let's say that there's a speaker from China, and Ji Hong, and I don't know if that's a female name or a male name, or yeah. So that tends to be why the custom is there. Okay, well, thank you very much for having me. I really appreciate getting the chance to talk to you a little bit about our department at George Washington University. George Washington, as you probably know, is one of the key figures in the founding of the United States. He's one of the national heroes in our founding story. And because of that, there are so many things named after Washington in the United States, and it would be you'd be very much forgiven to get mixed up with which university is ours versus the other universities that are called Washington. So there is a University of Washington in Washington State. That's not us. There's also Washington University in St. Louis. That's also not us. We're George Washington University. We're in Washington, D.C., like the capital of the United States. That's us here. So you're totally reasonable to get us mixed up with a few others. When I say we're in the capital, I mean we're literally just a few blocks from the White House, the presidential residence. This is an aerial view, and I'm trying to put an arrow as close as I could reasonably get to my office, but it's really a short walk to the White House. So we're right in the middle of things. It's a pretty vibrant campus to be on. Our physics building has some plaques outside that honor part of the history of our department, probably our two most famous professors that we've ever had at George Washington, Edward Teller and George Gamow. These are two nuclear physicists that shaped a lot about how we think about nuclear physics. George Gamow was born in Odessa. I think is a cool piece of trivia.
I can maybe interrupt you because
yes, please.
On previous lecture, when Professor Fomin was talking about traveling wave reactors, he mentioned a lot about Edward Teller and his impact on this research. So
Oh, fantastic.
is that exactly Axel is going on with this idea. So it's very good that the talks are connected together, you know, like that.
Well, that's a fortunate coincidence. I didn't realize. I think it's really cool that Teller and Gamov sat together. In the theory of nuclear beta decay, the Gamov-Teller selection rules are something that I teach to students, and
I'm sorry, one more remark.
Yes, please.
Gamov used to work in the School of Physics and Technology, where we are now here in Kharkiv. So this is also kind of the coincidence. And
Oh, that's great.
another coincidence like that. So Gamov used to work here in Kharkiv.
I know that he came to the United States in 1934 and joined the department and was here not for the majority of his career, but for a period of time. But one of the most exciting things that happened while he was at George Washington was in 1939, when the news of the first successful fission reaction had occurred. The announcement was made by Niels Bohr, and he chose to come to George Washington. It was sufficiently the center of nuclear physics in the United States for that announcement to be made. So this is something that we're very, very proud of. Our department now looks something like this. So this is the nuclear physics faculty. We have faculty also in astrophysics and in biophysics and in complex systems, but our nuclear group is probably the biggest and most well represented in our university. There's 10 full-time tenure track faculty, and we break down like this between our theory experts and our experimentalists. I'm an experimentalist, and Professor Afanasev is one of the leaders of the theory group. I'm going to talk to you today about some of the experimental efforts, and that shouldn't at all detract from the incredibly vibrant and exciting work that our theoretical colleagues are doing, but it's just not something I have a lot of expertise in. I go to them for help when I have theoretical problems. Our work is done not at the university campus, but we work at accelerators that are located across the United States and in Europe, and probably our biggest footprint projects in which we collaborate are at these three facilities. So on the left is Jefferson Laboratory, or Thomas Jefferson National Accelerator Facility. And that's an accelerator of electrons that's located in the United States on the East Coast and in a city called Newport News in the state of Virginia. So it's 300 kilometers or so from Washington. And it has a polarized electron beam that can be accelerated up to 11 giga electron volts. And this beam can be directed into several different experimental halls, but it can also be sent to a production target to make a polarized photon beam. So we also have the ability to do high energy gamma ray scattering experiments and photo production experiments at this accelerator. Jefferson Lab happens to be where I do most of my research, and I'm a member of two experimental collaborations there called CLASS and GlueX. And I'll talk to you today about one of the projects I'm working on with CLASS. The middle column is called the Triangle University's Nuclear Laboratory, or Tunnel. And this is a nuclear facility also in the United States, in the state of North Carolina. And it hosts a really cool accelerator called Higgs, or the High Intensity Gamma Ray Source. It's a free electron laser that using Compton backscattering can produce a high intensity and energy tuned photon beam in the 1 to 100 MeV energy range. So this is a lot lower energy than at Jefferson Lab, but it's useful for different kinds of questions. Whereas in Jefferson Lab, we tend to break things apart because of this amount of energy. At Tunnel, this can be used to do lower energy excitations. For example, you can do Compton scattering, which can tell you something about how polarizable the proton is, or different nuclei are. The rightmost column is the Paul Scherrer Institute, PSI. This is in Villingen, Switzerland. It's close to Zurich. And there, among the incredible facilities they have a 590 MeV proton cyclotron, so an accelerator for protons, but this can be used to produce high intensity secondary beams of electrons, positrons, muons, and pions for a number of physics applications. One of the experiments that goes on there is called MUSE, and I'll talk to you about that today. It's not an experiment I work on, but some of my experimental colleagues work on this. I thought what would be interesting would be to talk about two example questions that we would like to tackle as nuclear experimentalists. And we can talk about what experiments we use to go after them and how they work and how GW has a role in those. So the questions I thought were kind of the most fun, glamorous questions to address would be, what is the radius of the proton? And the second one is, why do quarks slow down inside nuclei? And this is one that's near and dear to my heart, and it's occupying most of my attention these past few years. So we'll start with the radius of the proton. So if you've been paying attention to nuclear physics news the past 10 years, you would know very well that the proton radius is currently experiencing a state of crisis. There's been a whole number of articles in both the scientific literature and in the popular press calling this a proton problem or a proton puzzle. And it has all to do with the fundamental quantity of what its radius is. Now, this seems like something we should have a pretty good handle on, but at the same time, it's awfully hard to go and measure the size of a proton. These illustrations of using different kinds of calipers to address the problem of proton width, it's actually a much more experimentally involved challenge to actually go and figure out what this radius is. I'll say that there's been two conventional techniques that have been used for decades. So for a very, very long time, our two techniques have been using electron-proton scattering measurements at accelerators. So you go to an accelerator, get an electron beam, accelerate it, shoot it off of protons, and analyze the data and use that to work back and figure out a proton radius. The alternative is to use hydrogen spectroscopy. So you get hydrogen atoms and you excite different atomic energy levels with lasers, and you measure the frequencies of these transitions. Based on combinations of frequencies, you can determine the proton radius based on how the proton's non-zero size perturbs these energy levels. Now, these two techniques have been done for a long time, and they give very, very consistent answers. We've assumed up until about 2010 that the radius of a proton was about 0.87 femtometers, or 10 to the minus 15 meters. And the uncertainty you can see is in the third digit with these techniques. However, in 2010, a new kind of technique became available, and that was muonic hydrogen spectroscopy. And this technique gave a startling result of about 0.03 of a femtometer smaller and a great deal more precision. It's much, much more certain of a number. And it's in disagreement with the previous techniques. And this is what puzzle has been befuddling nuclear physicists that we want to figure out. Now, to determine the proton radius from electron scattering, what we're trying to do is we're trying to measure a differential cross-section. So we're imagining accelerating an electron beam at a proton target, and we might put an electron detector somewhere at a certain scattering angle. And we might do an experiment where we count how many electrons go into the detector at that angle. And we might move the detector to different angles and measure how the angle affects the probability for electrons to go into our detector. Now, this probability is related to a quantity called differential cross-section. And you can think of it as just a probability of how likely it is to go at a forward angle or a more backward angle when the electron scatters from this proton. What's happening under the hood, you can imagine the electron beam is coming close to the proton, and the attractive positive charge of this proton is going to be pulling the electron. And so the electron will deviate from its original course. And so the question is, what is the probability of various angles of deviation? Here I'm showing the trajectory for a glancing collision. And you can imagine if the impact parameter was smaller, the electron might enter the volume of the proton and might be bent to a much more extreme angle. And so this is, you can see how this really gives us information about the size of the proton, because eventually the electrons will hit the proton or go into its volume, and that will affect the probability distribution of what angles come out, and that can tell us something about the proton's finite size. Now, it's not as simple as this. We have to actually use quantum field theory, and we think of things in terms of Feynman diagrams. And in electromagnetic scattering, the Feynman diagram that we think of is one photon exchange. So the electron exchanges a virtual photon, and that virtual photon samples the charge distribution. Now, in quantum field theory, we can actually try to calculate the differential cross-section or break it into pieces. And typically by convention, the pieces we break it into are the pieces we can calculate, the pieces that we know from quantum field theory. And that's if the electron is scattering from a point-like object. And the proton is not point-like, but at certain scales, it's close to point-like. It's very, very small. And then there's a perturbation on top of that, which we'll call the form factor. And this form factor encodes the charge distribution of the proton in terms of what we call Q squared, or it's the squared form momentum transfer. And so it's kind of a momentum space encoding of the proton's charge. And so anytime we're thinking about momentum space encoding, we realize that it's got to be something like a Fourier transform away from a position space encoding of that charge. So we can go measure the cross section for many different momentum transfers, and we can figure out what this form factor is, even if we can't calculate it from first principles. The radius of the proton by convention is defined as the slope of this form factor as momentum transfer goes to 0. And what does momentum transfer going to 0 mean? Well, low momentum transfer, or low Q squared, means the absolute most glancing collision possible, the smallest change in angle that the electron can have. So, it would be great if we could measure at Q squared of 0, but unfortunately that's not ever something experimentally that can be done. You'd just be blowing a beam right into your detector, which would not be good. And the other thing I want to point out is you're trying to measure a slope. So you actually want to have some non-zero measurements at non-zero Q squared or non-zero scattering angle, and you want to be able to extrapolate down to 0. So let's prove that that's really where the challenge of this technique is. You need to design an experiment to get to as small scattering angles as possible, and then you need to have the statistical confidence to do this extrapolation. The alternate technique, which we've had for a long time, is to look at the Lamb shift in hydrogen spectroscopy. So I'm drawing here a level diagram of the atomic levels in hydrogen. The Lamb shift is defined as the difference in energy between the 2s and 2p energy levels. And that difference is in large part caused by the fact that the electron can physically be inside the volume of the proton. And if so, it gets a big change in readjustment in energy relative to a point-like proton. Now, this is different for the s orbital and p orbital, because the s orbital being spherical, the p orbital being dumbbell shaped, they have different probabilities of being in the proton. So they get different penalties or enhancements for being inside the proton's volume. So there's a slight difference in energy. That energy difference should be proportional to the proton's size. And we try to go measure this. Now, actually measuring the Lamb shift directly is that transition is very, very difficult to do. But a lot of times what you can do is you can measure a combination of transitions to higher states. And by working out the frequencies to various combinations of higher transitions, you can set up a system of equations with some unknowns, and you can work out what the Lamb shift is. Now, the Lamb shift is hard to measure. And one of the ideas that was made to make it easier to measure was to switch from electronic or regular hydrogen to muonic hydrogen. And so in electronic hydrogen, that's regular hydrogen. We have an electron orbiting a proton. That's a hydrogen atom. In muonic hydrogen, you replace that electron with a muon. A muon's an unstable particle that's got the same quantum numbers as the electron, but it's got a lot more mass. And because it has a lot more mass, the cloud that it forms around the proton is much, much smaller. And that means the muon rather, has a much higher probability to be inside the proton than its electronic counterpart. And that makes the Lamb shift way bigger. Now, the cost of using muonic hydrogen is that you have to, first of all, make unstable muon particles. You have to slow them down from whatever accelerator you use to create them. So you create them at an accelerator moving fast. You have to slow them. You have to capture them on protons. And then before they decay, which takes something like microseconds, you have to hit them with a laser to excite these various transitions to try to work out what the Lamb shift is. And it turns out this is a much bigger experimental hassle, but it gives a much, much, much more precise result. And the collaboration at PSI in 2010 published their first results looking at the Lamb shift and actually looking at two different hyperfine transitions within the muonic hydrogen Lamb shift, measured the frequency of those transitions, found the radius of the proton and found it to be small, which was startling. No one expected this. In fact, the collaboration that was looking for this actually looked in the wrong frequency band for a long time because they didn't expect the frequency to be as significantly different as it was. So this produces the puzzle. So we've measured in two techniques, a large radius, and one new technique, a small radius. What could possibly be going on? Well, I think there's really three options. One is that the proton radius really is small, and that would mean that both electronic hydrogen spectroscopy and electron scattering have to be wrong in some way. There has to be some unaccounted for effect that's biasing the results. It's possible, but we haven't found that effect yet. Second possibility is that the proton radius is actually really large and that there's some unknown bias in muon spectroscopy. And that seems to be unlikely because, again, the technique is much more robust. That Lamb shift is very, very big in muon spectroscopy. It's a lot easier to measure. So then the third possibility is that maybe muons and electrons somehow probe the proton differently. What if electrons and muons have different interactions in some way, which would be an example of lepton non-universality, some new element to our theory of the universe? That's really exciting. Especially, it's also really exciting because there's hints of it at some of the experiments at the Large Hadron Collider. So this would be a way of doing a low energy, finding low energy evidence that somehow is synchronous with high energy experiments. So distinguishing between these possibilities is really an effort that lots of people are invested in, and part of our team at George Washington is very much invested in. So up until now, we've done three kinds of measurements. We've done electron proton scattering, we've done hydrogen spectroscopy, we've done muon spectroscopy. The thing that's missing is muon proton scattering. It's never been done. And that would be a really, really interesting handle, because if you measure a large radius, this might tell us that there's some experimental issue going on between these different techniques. If you measure a small radius, it would be very, very good evidence that there's actually this lepton non-universality that would somehow be a property of our theory of everything. So that's what we want to do. And especially it would be even better if we could measure electron proton scattering at the same time. We could actually compare the two in the same experiment and verify that there's no experimental differences between the two measurements. So that is what the MUSE experiment is trying to pull off. No one has ever tried shooting muons at protons before to measure a radius. This is work at George Washington. The George Washington team is led by Professor Evangeline Downey, Professor Bill Briscoe. And so this is their work. It's not my own, but I'm going to brag about it for a little bit because it's a really cool experiment. They're also running their experiment at Paul Scher Institute. So this is the same place that the muon spectroscopy measurements were done. And they built their own detector system, and they brought it there, and that's where they're conducting their measurements. Now, the Paul Scher Institute has a beamline called PIM1 that can produce a mixed beam of electrons, muons, and pions, and they can do it in either charge state. Yes, please.
This experiment is running in Washington, right? In your university or not?
No, this is running in Switzerland.
Ah, okay.
The pieces of it were built in Washington and then brought to Switzerland.
Okay, so that was the question again.
So this beam is produced by protons hitting a production target, and lots of things are made as a result of these very, very violent collisions. And there are magnetic filters which bring some of the products of those collisions into a beam, and you can do it by charge state. So you can grab all the positively charged particles, you can grab all the negatively charged particles, but then in that beam, you have a mixture of different particles. However, what's really nice is they're very, very well separated in time. So I'm showing here basically an arrival time spectrum of when these particles arrive at the MUSE experiment. And you can see that the first thing to arrive would be in this case, the positrons, then would come the muons, then would come the pions, and they're basically ordered by mass. So you select by momentum, they come ordered in time by mass. And so you have the ability to do an experiment where you collect data on all three beam types simultaneously. So you get a measurement of each one of these, and you have unambiguous separation when you go back and look at your data. Because this beam is a secondary beam, the intensity is rather low. You don't get very many particles going through, and it's also not very well focused. And that means to do a precise measurement, you actually have to track every incoming beam particle in. So there's a number of detectors that are arranged in front of the hydrogen target that allow a precise determination of the incoming beam angle and incoming beam position, so that one can reconstruct a very, very good scattering angle and get a momentum transfer very accurately. So these detectors are a beam hodoscope, and that's really a very, very good detector for arrival time. And I talked about separating particles by arrival time. That's very, very crucial with this role that this beam hodoscope plays. The next set of detectors is called the GEM telescope. GEMs are a gas electron multiplier detector. They're basically a detector that can determine the position of particles that pass through them. And this allows a very, very precise determination of the angle of the incoming beam. And then on the outside are what are called veto scintillators. They basically try to prevent triggering on events or any sort of events where the beam is way off axis, if it's steered very, very badly, because you don't want the beam to be hitting other material around your target. And so you think you have a proton collision, but really you have a collision on, say, an aluminum nucleus. That would be a background you want to avoid. So that's the purpose of the veto scintillators. And eventually you get to a cryogenic hydrogen cell, which is a liquid hydrogen target, which is our source of protons for this experiment. The target is surrounded by these huge planes to try to make as large an acceptance detector as possible. And again, with a secondary beam, the intensity is rather small. So you really try to win that back by using the largest possible detectors to cover as much area as possible. You can see the detectors are arranged in two big panels. And so this allows one to do a coincidence measurement. So you can measure the scattered particle on one side, and you can measure the recoiling proton that got a big momentum kick from the beam on the other side of the detector. The detectors are tracking detectors, which are straw tube trackers, basically measure the positions of trajectories as particles go by, and then timing detectors that basically allow measurement of the flight time, which is really crucial for verifying the particle identity of the scattered particle. So you want to separate protons from muons or vice versa, you need timing. MUSE was proposed in 2011. So this is already a decade-old experiment. It was proposed in response to the muonic hydrogen measurements. And it took a number of years to secure funding and to begin detector construction, and then proceed with commissioning in Switzerland. And right as the commissioning was finishing, that's when COVID happened. So there's about a year delay. But I'm happy to report that this past year was the first production data at the lowest beam energy setting. And the next couple of years are going to see additional production data at the higher beam energy settings. And it's I believe, on the order of 6 months of additional production that's still remaining.
And until what energies will it work? What is the maximum energy here?
Well, there's 3 beam settings for this beam line, but the key variable is momentum transfer. So for each beam setting, you can get a range of momentum transfers depending on the angle of the scattered particle. So the lowest energy setting will get you also the lowest momentum transfer. But again, the game plan is to try to extrapolate. You have to do an extrapolation, which means you need a slope, which means you need multiple energies to try to actually get some slope information to do this extrapolation. So the key point is the one that we've taken. It's one that's been taken already, but these other are necessary to do the extrapolation.
I have a small question.
Please.
Well, basically, you say that proton is, well, has some kind of crisis about the size of a proton. But to me, if you take into consideration quantum mechanics, you can say that all these calculations must have some probabilistic nature. Well, what I mean is all these calculations must be, well, they're just probable calculations, not exact.
So the conclusion is that we should measure a different proton radius with different probability on each experiment.
Yes, I do believe so.
Yeah, I think that runs into trouble because of the way you define eigenstates. So I think we believe to good credibility that the proton is an eigenstate of our universe's Hamiltonian. So our universe does have some, we believe in quantum field theory that our universe has some Hamiltonian and that the proton is one of the states in that Hamilton, one of the stationary states. And then when you have a stationary state, any operators that commute with the Hamiltonian should give a constant value. There should be no, there shouldn't be any probability distribution anymore. So for example, the proton has a consistent mass. We're very confident the proton's mass is 938 mega electron volts c squared. So that doesn't seem to have probability. Now the question is the field theory of our universe one that for which the radius is an eigenstate? And I think that's an open question. But it is interesting that one technique goes consistently low and another technique goes consistently high. It doesn't seem to be probabilistic. It seems to be quite deterministic there. So I don't pretend to know the answer to this. I think this is still very much open, but I raise these points for you to consider.
Understood.
Anyone have other questions they'd like to ask now? Okay. We'll continue. Here's the sensitivity that can be attained in μ's as a function of momentum transfer for the ratio of the cross-section for electron beam scattering and muon beam scattering. And you can see that the ratio is going to have precision that's well below 1% and probably much smaller systematic uncertainty as well. So this is really would be an achievement if we can accomplish this, and because it doesn't give us all that great absolute precision on the radius, but it gives us incredibly good precision on the difference between the electron measured radius and the muon measured radius, because many of the common systematic uncertainties cancel. And so the goal is to get to 0.5% precision on the radius difference in not 0.5%, but what's smaller than a femtometer? Anyway, 0.005 femtometers precision on the difference in the radius, which would be a really be sufficient to say if there's a difference between muons and electrons, which would be quite exciting if that were the case. Okay, that's all I wanted to say about proton radius. I'll pause. If anyone would like to ask their questions now, I'd be happy to do it. Otherwise, I'll go talk about a second puzzle, which is about how and why quarks slow down a nuclei. So any questions?
Maybe I could comment a little on Nikita's question about the deterministic or not. So I think in experimental technique, we measure kind of average values, and then they have some uncertainties. So that is not the point about quantum mechanical representation of classical views. That is almost the point of average values. Maybe, if I don't mistaken this way. So that was maybe the point, what was Nikita asking, and what is the answer for this question?
I think it's a really good answer.
That was just a remark to continue.
Okay, and I again encourage you to please interrupt. I'm always happy to stop and discuss. So the second example of a question that people in our department are working on is why quarks slow down in nuclei. And this is one that I work on a lot. It's near and dear to my heart. And so I'm actually now kind of more excited to talk about my own work. This work uses a slightly different reaction. It still uses electron scattering or scattering from a proton, but this reaction is called deep inelastic scattering. And deep inelastic scattering is when you crank up the energy transfer, the beam energy, the momentum transfer to the absolute limits. Instead of striking a proton and having the proton stay intact, something that's called elastic scattering, deep inelastic scattering, you try to transfer as much energy as possible to the proton and you blow it apart. And in the limit of infinite energy transfer and infinite momentum transfer, what you're really doing is the electron is scattering from a single constituent quark inside the proton and removing it in a quasi-elastic way. So you remove a quark. Now, quarks can never be found in isolation in nature, and as a consequence, both the remnant proton and the struck quark have to hadronize, and they do so producing a shower of particles that emerge. So it's not any single proton that's left; it's a shower of pions and kaons and antiprotons and whatever you produce in this very, very violent reaction. In elastic scattering, what this can tell us is about charge distributions and form factors, and in turn the proton radius, how the charge is distributed in space inside the protons. The electron's wave function is sampling the space of the proton. In deep inelastic scattering, the electron's wave function is only really telling us about the single quark that it struck. And for this, it's actually a very, very useful technique to learn about quark momentum distributions. Now, in the same way that in elastic scattering, we thought of the problem as scattering from a point-like object times some modification, some structure function, some form factor that is the part that we don't know ahead of time. It's the part we have to measure. The same thing is true for deep inelastic scattering. And we typically call the structure function here F2. And F2 is a function of a variable called, imaginatively, X. And what we conventionally define X to be is the fraction of the momentum carried by the quark that was struck when the proton is moving in an infinite momentum frame. It's kind of a weird variable to consider, so I do not blame you for saying, why do I have to think in terms of this X variable? But you can imagine it's sort of like a projection or a boost of the momentum carried by the quark in some longitudinal axis. And when you're striking a proton very, very violently, you're approaching the infinite momentum frame in some respects. So that's why X comes out of the equations and out of the math here. To give just a little quick tutorial of how X works, I'm going to show what the F2 structure function would look like in a graph on the right for various different models of the proton on the left. And so you can imagine if
I just want
yes,
to ask, do you call this kind of Bjorken variable or not?
Yes. Bjorken X, exactly. Yes.
That is the one, right?
That's exactly the one. Yes, exactly
okay.
right.
Just to understand the terminology. So, okay, thank you.
Perfect. Yes, if you're familiar with the Bjorken scaling variable or Bjorken X, or these are all the same thing. For this talk, I've just chosen the terminology X, but there's no difference between this X.
To make it clear, because maybe for students they listen it first, but just to make it clear for myself. Okay,
perfect. Thank you very much. The first model example I'm considering here is a proton with this one single quark. So here's, all the mass and all the momentum is carried by this one quark. And in that case, the structure function would be like a delta function at an X of 1. That single quark carries all the momentum all the time. And so that's a really trivial example of a structure function. Let's imagine that there's 3 non-interacting stationary quarks inside the proton. In that case, the structure function would be a delta function, would be at 1/3. So each one of these quarks carries 1/3 of the total momentum of the proton, and the structure function is, again, a trivial delta function. Now, imagine we allow the quarks to interact. They can exchange momentum with each other using gluons or some other force. This exchange of momentum will have the impact of producing a distribution so that not all quarks carry the same momentum at all times. And now we would expect to see the F2 structure function as being a distribution, maybe a Gaussian around 1/3. So on average, each of these 3 quarks has about 1/3 of the momentum. However, at any given moment, it might be more, it might be less. Now, in reality, what we've measured the proton structure function to be is sort of like this shape that I'm drawing here on the right. And the results of this is actually 2 things. You can see there's a component that's a little bit like the Gaussian. You can see a shoulder. And this is really caused by those 3 valence quarks in the proton exchanging momentum. But then you can see at very, very low momentum, the structure function just diverges. It goes up to infinity. And what is going on here is that the gluons that are being exchanged between quarks can actually split and produce quark-anti-quark pairs. And so this is what we call the quark gluon C component of the proton. And so you have a lot of low momentum quark anti-quark pairs, and it's very, very clear in the structure function. We see basically two regimes. We see a valence regime at high x, say x above 0.1, and we see a C regime at lower x. And so that's what we've learned about the proton. Now that's interesting by itself, but that's not specifically the puzzle I want to talk to you today about. I want to compare what happens when we look at structure functions for quarks inside nuclei. And the first caveat that I want to bring up is that the proton and neutron have slightly different structure functions because they have slightly different quark content. The proton's valence quarks are 2 up quarks and a down quark. The neutron's valence content is 1 up quark and 2 down quarks. The up quark has more charge than the down quark. And so when you do electromagnetic scattering, you find that the reaction proceeds much more favorably with the proton than the neutron, or not much more. I mean, you can see on the graph, it's 30% more, something like this. And so we have to acknowledge at any point we're going to talk about nuclei with has protons and neutrons, we have to sort of be aware that the neutron contributes less than the proton does to the total. Now, you could imagine looking at nuclei that are symmetric, for example, carbon-12 or the deuterium, which is 1 proton and 1 neutron. And it'd be a very, very reasonable expectation to measure the structure function for carbon and deuterium. And as long as you average per nucleon, you might expect that the structure function would be somewhere in between the proton or neutron curves. And when one measured this, however, in the 80s, there was actually a fairly strong difference. And so here I'm showing as a function of x, the F2 structure function weighted per nucleon for iron relative to deuterium. So again, if you figure all symmetric nuclei are about the same, you would expect this ratio to be flat at 1. And that's what's labeled with no change in quark motion. Instead, what this experiment measured is actually a decrease as you go into higher x. This experiment that measured this was called the European muon collaboration. They actually did this experiment with muon scattering, but that's not relevant to the story. What is relevant is EMC became the name of this effect. So this experiment has nothing to do with muons, or this effect has nothing. It's not, muons are not important to this effect. EMC is not important to this effect. But since the EMC experiment discovered it, we call this the EMC effect. So you're going to hear me use that terminology for the rest of the talk. So the EMC effect describes this difference in how quarks move in a heavy nucleus like iron versus a light nucleus like deuterium. And because there's a depletion of high momentum quarks, you can somehow say that the quarks in iron are somehow moving slower. They're somehow not moving with this much momentum relative to deuterium. Now that makes no sense. And the reason it's really surprising is because the amount of binding energy that's holding protons and neutrons into iron is, a couple of MeV, I think 8 MeV on average. The amount of energy transfer in deep inelastic scattering is multiple giga electron volts. It just doesn't make sense that a few mega electron volts of binding would affect a process that's occurring at giga electron volts. This is bizarre. And it's really a puzzle that's stumped us for what's coming on like 40 years now, I guess. So it's been 4 decades since we've found this effect, and we still don't have a really good handle on what causes it. It's been measured many, many times in many different nuclei. And so I'm showing data from light nuclei like helium-4 all the way to really heavy nuclei like gold. And you can see that all nuclei show the same kind of shape in the data, that in this valence region, X from about 0.2 to 0.8, you see a decreasing slope in the ratio relative to deuterium. So it seems to be in all nuclei. It was measured at Jefferson Lab at a little bit lower energy in light nuclei, but again, they see the same consistent picture. It seems to be a universal feature of nuclei. So what the heck is going on? To quantify the EMC effect, we found that the convention is to use the slope of this linear decrease, and that avoids normalization uncertainties. So that's sort of a more robust number. And so, for example, we would take data measured at SLAC, and for carbon, we'd fit a linear slope in the valence region, and we'd find that the magnitude of the EMC effect, we'd call it 0.32. Now, people have done calculations to figure out how much the fact that the protons and neutrons are moving in the nucleus, a process we call Fermi motion, affects things. And the answer is Fermi motion, does play a little bit of a role. It certainly is what causes this uptick at very high X, but it doesn't cause the full slope of the EMC effect. So this is not caused by just the nucleons in carbon moving differently than the nucleons in deuterium. There's something going on inside the protons themselves. So I'm going to illustrate this by some cartoons. You can imagine, so on left, I'm showing a free proton, free neutron. To explain the EMC effect, it's as if you put these protons and neutrons in a nucleus, they like swell a little bit. Their confinement volume increases, and that would produce a lower momentum distribution for the quarks inside. And so a lot of the theories that have tried to understand the EMC effects have considered the problem of what about the nuclear medium is causing these protons and neutrons to swell? And I would say that's still the conventional hypothesis. Now, I'm really interested in an alternative hypothesis. And that has to do with the fact that about 20% of nucleons at any given moment in large nuclei are participating in what's called a short-range correlation. Short-range correlation is where two nucleons get very, very close together, like closer than the radii, closer than 0.8 femtometers, say. And this, by uncertainty principle, produces a very, very large relative momentum. And this large relative momentum distribution seems to be universal across nuclei, which means it's really a two-body interaction rather than a nuclear interaction. It has nothing to do with the nuclear structure. It has really to do with the interactions when two nucleons get very, very close together. We've been able to study this in a variety of ways. And one of the cool ones is you can actually do experiments where you knock one of these nucleons out of a nucleus, and you can get the other one to come along for the ride. It's something we call correlated emission. And that's been a really useful way of studying properties of these correlations. One of the big findings of these studies is that about 90% of these correlated pairs of nucleons are proton-neutron. So it's less likely than you'd expect to find a proton-proton or neutron-neutron pair. They do occur, but they're much less likely to occur. Proton-neutron seems to be favored. So the hypothesis that has me really intrigued is, what if actually most protons and neutrons in the nucleus don't change their structure at all? Their quarks are doing the same thing they would do as if they were free. But if a few of the nucleons changed a dramatic amount, and these would be the nucleons participating in one of these short-range correlations, what if these nucleons have their quarks change momentum distribution in a dramatic way? Now, when we measure the EMC effect, we're measuring the average. We're measuring the aggregate over all nucleons. And so it's possible that if the effect size were large enough for these correlated nucleons, it might average out to something that's consistent with what we're seeing in the data. Some pieces of evidence that support this. So one is, if you try to ascertain the relative number of correlations in a nucleus, and you then compare that to the EMC slope, it's like weirdly linear. So that's an intriguing curiosity. Another way I've studied this is probably might be the most impactful paper I ever write in my career. I tried to build a model to test this hypothesis that the modification per correlated pair should be universal. If we think that correlations are really dominated by strong interactions between one nucleon and another nucleon, the nuclear structure shouldn't matter. It shouldn't matter if this pair is in gold or helium. The modification of the quark should be the same in all of these nuclei. And so we built a model. We said that the structure function for a nucleus is going to be made up of some of the protons, which are unmodified, some neutrons, which are unmodified, and some pairs which get modified, have some new structure function because their quarks are moving differently. And actually, it's maybe a little bit more tidy to write it like this, where we parameterize it in terms of how much the proton structure function and how much the neutron structure function are changing. Now, in this model, we're just assuming that all correlated pairs are proton-neutron pairs, just because they're already the vast majority. So this is a simplification that aims to make the math a little easier. Now, you can see the neutron structure function appears in the equation, and we actually have a hard time measuring this because we don't have a way to make a free neutron target. And so we actually use deuterium to replace the neutron reference. So we rewrite the deuterium structure function in terms of the neutron, we loop that back in, we do a little math, and we come up with this equality, which is like the heart of our prediction. So on the left-hand side, I've arranged all the terms so that all the nucleus dependent stuff is on the left. So anything that would change when you move from, say, helium to carbon to iron to gold, that's on the left-hand side. You can see there's the number of short-range correlated pairs, the F2 structure function, the proton number, the neutron number, all that stuff on the left. On the right-hand side, everything here should be unchanging as you move from nucleus to nucleus. There's deuterium as a reference, but basically on the numerator, you have the change in structure function per correlated pair. And so this is what we tested. Is it possible that all of the nucleus dependent stuff on the left-hand side can somehow conspire to make something that's universal on the right-hand side? So just to remind everyone, this is the size of the EMC effect from helium-3 all the way to lead. However, when you take this data and you rearrange it according to the form on the last slide, this is what you get. The modification per pair seems to be pretty universal, which is a pretty cool piece of evidence supporting this alternative hypothesis. So the question is, how can we go confirm this? How can we go measure this specifically? Now, I've said that when we measure the EMC effect, we're measuring all the protons and all the neutrons in aggregate. We're averaging over them. What we want to do is we want to isolate times when we hit nucleons that are participating in a correlation. And the way that we do this is by actually tagging the correlated spectator. So if we can detect the backward recoiling nucleon that wasn't hit, we can correlate that to the momentum of the quarks in the nucleon that we did hit. So we have to both detect the scattered electron, which tells us about the quark that we hit, and we also want to detect a backward recoiling nucleon, in this case a neutron, to figure out the initial state of that struck nucleon. And by initial state, really we want to measure its momentum, because if we know that we're in a low momentum state, that means the correlation, the pair was sort of widely spaced. But if we measure high momentum, it implies that they were more tightly spaced. So we want to check how quark distributions change with this initial state. So I'll just flip back and forth a little bit here. So that's why we want to measure this nucleon momentum. For this, we designed an experiment that's based around a backward angle neutron detector, and it's embedded in the class 12 spectrometer. And the idea is we'll do deep inelastic scattering on deuterium. We'll measure the scattered electron in the standard detectors that are part of this experiment, but we'll add a backward neutron detector to try to catch spectator neutrons. This experiment took place at Jefferson Labs. This is a big electron accelerator in Newport News in the United States. And there's a bunch of different experimental halls. We have the electron beam directed toward Hall B, and the equipment in Hall B is this amazing detector system called CLASS. And it's huge. It's like 3 stories high. It's like the size of a big house. And this is just a piece of it. I can't fit all of it in one picture. Here's another piece of it. You can see the levels of scaffolding that are next to this big detector. And you can see people for scale. So this is a great detector for detecting particles that go forward. And we wanted to add a detector for particles going backward. And that detector is called BAND. There's like a 2-meter array of plastic scintillator bars. And plastic scintillator is a decent neutron detector. These scintillator bars are read out with photomultipliers on each end. And by comparing the times of the two detector of the signals, we can learn 2 things. So the average time tells us about the flight time of the neutron, and that tells us about its momentum. The time difference tells us about the hit position, if the hit of the neutron occurred more to left or more to the right. And so these 2 pieces of information give us the complete picture. This is what the scintillator looked like when it arrived at a crate in the lab. It was like, I think, 2.5 tons of scintillator plastic. We assembled all of these modules, and we used the coupling to the photomultiplier tubes was accomplished by this glue that's optically transparent, but it cures with an ultraviolet light. So we had this ultraviolet lamp, and we were gluing these assemblies together in order to build the final module. And we stacked it into a big array in a big frame, and then craned it in place so that the beamline would actually pass through the detector and go into the target in order to deliver the beam onto the deuterium target. Here's our team after installation was complete, and the beamline actually is going to go right through that hole in the detector, but it's yet to be installed. So in this experiment, construction installation took place in 2018. We had 2 data taking runs, 2019 and 2020, and we're furiously underway with data analysis, and we're pretty close to having a result. I can't tell you the final answer yet because it's not approved for release, but I want you to stay tuned, because in the next few months, we'll probably have something. Just to show you a couple of vanity pics, here's basically what a time of flight spectrum looks like in our detector, and you can see a very, very clear photon peak. So these are particles that arrive at the speed of light, and beyond that, you can see neutrons sitting on top of a large background. You'll also notice that there are some signals in our time spectrum that arrive as if they moved faster than the speed of light. Now, that's obviously impossible. What's going on is that there is random background producing neutrons in the room that's like not correlated in time with the electron beam. And this is a random background that we have to deal with. However, if we look at electrons that occur faster than the speed of light, so to speak, we know that they're background. And so that tells us a little bit about the distributions. There's not many of them, but we can actually produce a larger sample of background to do background subtraction by doing event mixing. We can take a random background neutron and pair it with a random electron somewhere else in the experiment, some other time. And that can give us a much, much bigger statistical sample to model our background and allow it to subtract it away so we can access purely the neutron signal events we want. Here's just a anticipated precision. So the x-axis is neutron momentum. The y-axis is the change between the bound proton structure and the free proton structure at a Bjorken x of about 0.6. These are the data that we think we can put on this graph. And then I've shown a number of theory curves. And the point of these theory curves is just to show that the theory is just all over the place. There are all sorts of predictions that span a huge range, which means this data is really useful. This data will actually be able to say something that and verify some theories are correct, rule out others, and actually give us some constraints on this graph. Okay, so to recap quickly before time runs out, I've talked about 2 example questions about that we're working on in our department. So what is the radius of the proton? Maybe big, maybe small, but Muse is going to tell us soon what the origin of that difference is. And the second question is, why do quarks slow down in nuclei? And I think it's possible that it's due to short-range correlations, and the band experiment is going to test this hypothesis. I just want to close saying one thing, is that the next big accelerator that's going to be built in the United States is going to be the electron-ion collider. It's going to be a polarized electron storage ring and colliding against a hadron storage ring. And construction is supposed to start in a couple of years, and first beam is sooner than we maybe feel. It's probably 2030 to 2034, we're going to be starting taking data. So anybody that builds a career in nuclear physics, this is going to be one of the major accelerators in the landscape. George Washington has a big role in the development of this project. And so if anyone one day comes to George Washington University, you can expect this to be a large part of their portfolio in their experimental campaigns. With that, thank you very much for your attention. I'm happily take the questions that you have.
Okay, thank you very much, Axel. That was a really interesting talk. Guys, please, questions to Axel.
I have a question about, well, you said that, there's possibility that there's a new interaction between, well, a new type of interaction between proton-electron and muon-electron. Is this some type of new interaction, or some kind of already known interactions, like electrical interactions? Well,
it would have to be a new interaction. And the question is, what is that new interaction? And there are some different candidates. So we know that there's some physical fields or particles that are undiscovered, and they include the origin of, for example, dark matter, or the possibility of supersymmetry, or a number of other the theta, the strong CP problem. There's a number of problems that seem to necessitate additional interactions that we've never discovered. And the question is one of these also the origin of this electron-muon difference? For example, if there were a very, very heavy supersymmetric particle that was responsible for dark matter, that was maybe just above the weak scale, or maybe just above the region that the Large Hadron Collider could access, this could still produce differences in how the electron and how the muon interact because of loop corrections. So maybe the electromagnetic force is the dominant, is the force that these electrons and muons are interacting. But the virtual photons in this interaction can make loops. They could make particle-antiparticle pairs as they propagate. And these loops, if they have massive, heavy, undiscovered particles running around, have the possibility to affect electrons and muons differently. So there's lots of options, but no overwhelming candidate, I would say.
Understood. I just thought that, well, maybe this new interaction is just some kind of linear combination of previous four.
I don't have the theoretical abilities to tell you yes or no. That's a good question for some of my colleagues. I don't want to rule anything out because people are very creative with the mathematical ways they can formulate the theories. So probably there's a way to do it.
Okay, thank you, Axel. Maybe more questions or comments about this talk?
Can I ask one?
Absolutely.
You told about the deuterium nucleus that can form inside of not nucleus that can form inside of bigger nucleus. I mean, when you said that we have only a few protons and neutrons that interact strongly, yes?
Yes.
Don't you thought about that there can be also some alphas, maybe not only deuteriums?
Yes. That is a very tantalizing possibility. We've never been able to experimentally observe short range 4-nucleon clusters. So it's very, very clear that there are alphas in heavy nuclei, but it's not clear if they are what I would say short range or highly modified, in the sense that we can measure the EMC effect in an alpha particle in helium-4 nucleus, and it's not that big. So just having a preformed alpha in the nucleus isn't enough. You need the alpha to also be in a very, very tightly compact, short range, small size configuration to produce some big modification. How we would experimentally get at that, I don't think we're technologically there yet. I think the next goal will be to isolate 3-nucleon correlations. And that's another experiment I'm working on, but is a little bit, probably a year to 2 years away from having results.
Good, thank you.
Another question. Well, in experiments, did you consider some relativistic particles or some quasi-classical particles?
At the energy ranges I'm working at, nearly everything we do is fully relativistic, if not ultra relativistic.
Understood.
Okay, so if we don't have any more questions, so maybe we can thank Alex one more time for the nice talk, and guys, feel free to contact me if you have some questions or about the opportunities in Washington University. We also have strong connection. Axel is experimentalist, but we also are connected to the theory group of Washington University. So we can contact, and if there are some proposals or any further collaboration, so we are open also for this.
It's wonderful to hear.
Okay, so thank you, Axel. You now can be free, and I'll tell some extra information to my students. Okay.
Thank you all. Appreciate the opportunity to talk with you. Have a good day.
Yes, you too, Axel. Thank you so much.
Bye.
Bye. Ребята, ну, как бы, да, закончили мы практику, вот, да. Значит, опять по этому дню вышли вам какие-то вопросы, в принципе, ну, как вы себя чувствуете? Нормально, тяжело, мало, много?
Более-менее.
Что?
Более-менее. Правда, про предыдущая презентация, не та, которая была сейчас, а предыдущая,
Мгм.
с челиком из Румынии. Я немного не понял вообще ничего.
Так.
Даже не связано с языком. Это просто какие-то, ну,
Они моделируют, делают эти самые, как они, панели солнечные, да, и моделируют, каким образом там влияет среда на их эффективность и так далее. Достаточно понятные вещи, не сильно такие фундаментальные, как, допустим, вот, допустим, как Axel рассказывает, да, ну, он как бы экспериментатор, там у нас и теоретическая группа, то есть, ну, есть контакты. То есть я к чему говорю? Вы же помните, мы с того начинали, что практика для того, чтобы расширить ваш кругозор, чтобы вы понимали, что есть и такие, кто-то больше любит фундаментально. Вот как даже, смотрите, такая как девочка, как Арина, которая вам на первом часе, да, рассказывала. Казалось бы, элементарные вещи, но ну, как бы нужно, есть и над чем вам позадуматься, и много информации новой получать. Вот у этого парня, который с Румынии, у него проекты очень приближенные к индустрии, понимаете, вот этот Ph.D, который вниз уходит в индустрии, да, то есть у него применение явно и так далее. Здесь идет более фундаментальная наука, которая спонсируется там уже на государственном уровне, это вопросы электроэнергетики, будущего и так далее. То есть вот, например, как бы начальник Акселя, он работает непосредственно в департаменте энергетики США. Это наш как бы выпускник физтеховский, у нас налажены там, ну, в общем-то, контакты, и многие, даже мои одногруппники в свое время уезжали по этой программе в Вашингтон. То есть вот Сергей Петрович по ядерным реакторам, он работает больше с Сергеем Барсуком по французским. Видели, он там говорил, что во Франции очень сильно развита ядерная энергетика, очень много реакторов, они на этом как бы, это опять же таки, это уровень уже государственных программ, а не, ну, так сказать, локальных, да. То есть, ну вот, ну, вы как бы еще не на том уровне, чтобы доходить до всего этого, но вот на уровне вот Арина вам рассказала, как вообще построить свое, ну, как бы будущее в научном или же не в научном плане. Тут уже будет как бы непосредственный ваш выбор. Наша задача в этом смысле вас, ну, предоставить вам этот выбор и, в принципе, сориентировать в том или ином направлении. Но без усердной работы, вы думаете просто так, вот так вот все. То есть каждый из этих ребят каждый день стабильно работает над поставленными задачами. То есть тут надо уже становиться вам серьезнее. Я не говорю, что не надо отдыхать, не говорю, что не надо, ну, как бы проводить время и для себя, так сказать, но тем не менее уже потихоньку взрослеете, вы уже не первый курс, начинайте, так сказать, трезво оценивать жизнь и помните, что всегда вот мы как бы вам можем в том или ином варианте, какие силы у нас есть, вас, ну, вам помочь, вас устроить, так сказать, в будущее, чтобы вы в будущее вошли, так сказать, легко. Вот. Ну, как-то так. Еще какие, может, вопросы? Ну, если вопросов, ребята, нету, тогда спасибо вам за внимание. Про школу сказал? Про школу сказал. Кому сказать? Про школу, вот это вопрос к тому, что надо работать.
Не покажу. Здравствуйте. Сморцов. Кто еще? Ясмина. Барышева. Присылайте свои планы по лекциям, практикам. Москвитин тоже. Не стесняйтесь. Уже все, уже последняя неделя.
Не оставляйте на потом. Знаете, все, я хочу сказать, просто не оставляйте на потом то, что можно сделать сейчас. Настя, все нормально? Вы работаете? Нет? Яся. Настя, Яся.
Хорошо.
Все хорошо, да? Ну все, ладно, не будем занимать друг друга время. Еще раз, значит, спасибо. Все, там дальше по расписанию. У вас с плазмистами есть контакт, да? Я правильно понял? Потому что я тогда не выложил, помните, по плазме, по кафедре, там, ссылку. Вы говорите, мы уже работаем. С плазмистами есть контакт, да?
Да, нам на почту выслали.
Ага. Ну все, ну я еще, может, продублирую. Ладно, все, ребята, тогда see you later, have a good time. Всего доброго.